the characteristic Cauchy problem. Let's work on.
So, good morning, everyone. My aim is to present you a review of the characteristic Cauchy problem in general relativity. There's something that you've heard a lot already by now, or some of you know, that Einstein equations, which are equations for the Lorentzian metric, have a hyperbolic character. That's actually not an obvious fact, but it was discovered by Ivan Shekebria some 72 years ago. Talking about Ivan, let me just mention that Ivan had her 100th birthday in December last year. So she discovered this interesting and fundamental fact for us that Einstein equations can be written as a set of hyperbolic equations. And she was studying something called the space-like Cauchy problem. So in this case, you get also a set of constraint equations on a space-like initial data surface. Well, here in this picture, you can see Ivan in a conference we had in Cauchy some 22 years ago. It was to celebrate. This person you recognize, it's your student, Robert Bartnik. Yeah, right. Well, I'm sitting here a bit younger than now. This is Bobby Bag and Helmut Friedrich, and this is the money man, so the person who is paying for the conference. Right, so there is this space-like Cauchy problem where you give a metric on a space-like surface and it's time derivative. But there's another way of doing it, which is the characteristic Cauchy problem. That's what I'm going to tell you more about right now. Summarizing what she said is what Ivan proved, right? Einstein equations can be constructed by solving a Cauchy problem. And this has been then complemented by another fundamental theorem that, you get existence and uniqueness of a maximal solution with some good properties. Whether this maximal is actually the end of the story, well, you've heard yesterday from Cauchy for explaining why it's not, but this is related to the strong cosmic censorship conjecture. But at this stage, let me just pass to the characteristic Cauchy problem. So the characteristic Cauchy problem, what you do is you just have two null hypersurfaces which intersect. You need two for reasons which might become clear later, but one is not good enough. Somehow it should be clear that if you want to know what the solution is here, you need the data to the past, and if you only had one surface, then you wouldn't have enough data to solve your problem. So one way is just to have two transversely intersecting null hypersurfaces. Another one is just to have a light cone. So the characteristic hypersurface is the light cone, and then it ends at a T. This problem has a long history. Sachs is the first paper which, to my knowledge, treats this in a satisfactory way. So 62, this was shortly after the famous Bondi-Metzner-Sachs paper on the existence of gravitational variation, or how to formulate the problem of radiation in a nonlinear context, and he quickly realized that this has something to do with the characteristic Cauchy problem. He quotes Darmois from the well before 30-something, I think. But I mean, I've looked at this Darmois paper. I certainly cannot see anything remotely related to the setup that he's doing. So certainly Darmois had a lot of interesting information in his paper, but I think the first one is really Sachs. And in fact, Sachs does everything that that we know as far as the formalist is concerned. So, for example, the basic theorem which I'm going to present to you is that of Rendell. And so what Rendell does is to add a lot of machinery to the setup that already is in SAS. Now, what about the other papers here? Well, then Cagnac and Müller-zu-Hagen were interested in trying to prove the evolution theorems which go with this Cauchy problem. They were not available at the time. So there are some results there, but it's far from setting the problem. Then Christodoulou and Müller-zu-Hagen wrote a paper which corrects some gaps or some mistakes in this Müller-zu-Hagen-Seifert papers, but it's again about just question of being able to solve the equations rather than solving the whole problem as we know it in general relativity. And then the key theorem was then Rendell in 1990, which gives an existence theorem for the whole problem. So Einstein equations, he tells you how to set up the constraints and get an evolution. And what he does is he proves a theorem that if you have two intersecting hypersurfaces like that, then you get a neighborhood of the intersection where you get a solution of the equations. So we started looking at this with Ivan and Jose Maria Martin Garcia in 2009, and we noticed an amusing fact which has some kind of fundamental flavor, that you can use this characteristic Cauchy problem to show that Einstein equations contract things. Right? So they're only contracting. That's something we kind of know. They attract things, but here there's a clear illustration that they contract space-time. And the way to think about this is as follows. You take a light cone. So you take a point in a space-time which satisfies Einstein equations with positive energy density. And from this point, you shoot no geodesics, you get the light cone of this problem. Now, each of these geodesics has an affine parameter on it, and of course, you can change these affine parameters at will. But here, when you're starting from a point, you have a natural parametrization, or a family of natural parametrization. But it is as follows. You take this point, you choose a time-like vector, and you normalize your affine parameter on each generator so that the product of the initial tangent with the unit time-like be -1, right? So fixed product with the initial tangent. So this normalizes the affine parameter on each generators, and then you go to constant defined time surfaces. So you get a family of natural sections of the light cone. You measure the area, and the theorem is that the area of these surfaces is smaller than the one in Minkowski, unless you are in Minkowski. So that's so this is a clear illustration that the metric kind of gets squashed by the Einstein equations. Good. So that's an observation we made here. So we were interested in showing that solutions of this problem exist, and there are various difficulties at the tip. So at the time we didn't manage to do this, but we observed this interesting, I hope, fact about Einstein equations. Good. So now what happened is that we kept working on this. We kept working on this, and what Rendell did was to prove this theorem in dimension 3+1. We generalize it into all dimensions, so to get this neighborhood for two hypersurfaces. Then Luke improved this in 2011. Namely, rather than getting a neighborhood of this point, you get a whole neighborhood of of the surfaces, right? So that's the first now descent theorem, really, what you want, right? So you give initial data of the surfaces, you want an intersection. Sorry about this. You want a neighborhood of the initial data, not a neighborhood of part of your initial data. So that's Luke's theorem, again in 3+1. And his proof has really a 3+1 flavor because he's using a set of other equations which were at the time justified and derived in 3+1. Well, with Aurore Cabet and Roger Tanier-Wafo, we showed that this neighborhood that you see here, the way it's written here, it looks like it stops, but it doesn't stop. It just gets thinner and thinner as you go up, right? So if you think about this picture, if you wanted to go further, you'll get a strip which is like that, and you go a little further, you get a strip which is thinner and thinner. That's the kind of theorems you get. And now, if you are in the asymptotic flat context, you'd like to go all the way to infinity, and the Luke's theorem doesn't give you a neighborhood of in the conformal space-time, but so what we showed that you can, if you are in the asymptotic flat context, then you can go, you get a piece of sprite out of this rather than something which kind of gets thinner and thinner when you're going to infinity. So finally, we managed to do the Kohn problem. So as I mentioned, there are various problems, analytic problems here at the tip, but so eventually there is a theorem which tells you that whenever you have a smooth, initial data on a light cone, which are coming from some smooth metric, then there exists a vacuum solution inside, which realizes this data. So now this Kohn problem is, and of course you get a neighborhood of the Kohn, and if you go to infinity, you get a piece of spray and so forth. So this is more or less settled. Now, so this neighborhood in all dimensions, then as I mentioned that this neighborhood theorem, so get a neighborhood here, was done by Luke in 3+1, and then in 2018 they showed that you can generalize the equations that Luke was using to all dimensions and get the result in all dimensions. And so what's the new exciting result here? That's 3 years ago. The C2 characteristic bluing near 3+1 in Cauchy. So most of the rest of my talk will be about this problem. So what is this about? Suppose you have a yellow spacetime here with a known metric. So it has its characteristic data here. It's coming from, obviously you need some more data to determine this spacetime, but when you have this yellow spacetime with a no boundary like that, you have some data here concerning spacetime. And you have another green spacetime here, which has, again, which is known, let's say it's supposed vacuum Einstein equations, 3+1, that's what they were assuming. And actually, they were assuming that the metrics were not far from a light cone in Minkowski spacetime. So you have these two spacetimes, and you're asking your question: can I find a bigger spacetime where the Einstein equations are satisfied, where these things will be exactly as they are in this spacetime? Okay? So can you just connect? So and the idea is to connect now. This you have a null hypersurface here, which is to the past of your spacetime. You have a null hypersurface here, which is to the future of your spacetime. And you want to find a connecting null data here, which would allow you to get a full spacetime out of this. So this is the problem. And I'm going to show you some applications of this. So it's not only, well, I think it's just interesting conceptually to be able to do this, but not only it is interesting, but it allows you to do things afterwards. So that's why it's interesting. And they gave a partial answer to this. And let me emphasize this C2 thing. And I'm going to explain, what this C2 means, because it's a little misleading. The C2 is actually not really C2. So let me go on. But that's the question, right? Can you just do something like that? We actually generalize this for any k, and I'm going to explain why it's important to have this k larger than 2. But let me just go on and present you or review how do you do this and what's the setup and what are the equations and so forth. So if you want to learn more about this, I think that's an excellent introduction to the subject, this paper. And so what are the characteristic initial data in general relativity? So the thing is, well, you need this characteristic. Well, you need 2 maybe, right? But I mean, so each of these surfaces carries some set of data, and so this would be in 4 dimensions, and this would be a 3-dimensional manifold, and it's going to carry a tensor which has signature 0++. In the space-like case, you would get a Riemannian metric. Here, you get a tensor which is degenerate because there is no direction. So this is, you can think of this as a degenerate metric. Some people call this, but of course it's nonsense because the metric is not degenerate by definition. So you have this induced, if you had a space-time, that would be induced tensor which has a kernel. And now on, so at each point on this null, on this null hypersurface, you have this null direction, and so therefore you have a field of null vectors. So you can take the integral curves, so you have a 1-dimensional bundle of degenerate directions. So because at each point you have a line, and it's a 1-dimensional tangent space. So at each point you have a 1-dimensional bundle of degenerate directions, and you can then look at a connection on this bundle. So this lambda here is a connection on this bundle, and that's data. So it's not obvious that you need that, but that's how things work. And so what's a connection on a 1-dimensional bundle? Christoffel symbols have 3 indices, and you're in 1 dimensions, so it's only one number, right? So one function. So they have a function which transforms as a connection. So that's your setup. Now, it's nice to use adapted coordinates to see how this works. So you have your space-time metric, and u equals 0 is your null hypersurface. So you write then this metric on this null hypersurface. Now, because dr is, so here I'm taking dr to be along the null direction, so therefore that's a 0 length object which has no, so there's a 0 here. Well, actually, that's a property of null surfaces that the null is actually normal to the surface. So if the xa's are the remaining coordinates here, then there should be no components here, right? So that's how in adapted coordinates your metric will look like. So this would be a 2-dimensional. At each r, that's a 2-dimensional metric. In higher dimensions, you get n minus 1. Well, more of that, right? So you have this is the metric from the previous slide, right? So this is a metric on the which has this null kernel. Now there is something called the expansion scalar. Now this expansion scalar, I'm going to write it as theta, so you just take the derivative of this metric. I'm writing g check here so just to differentiated from G. So G check is this thing, and its inverse is G check, right? So just take the derivative in the null direction of your two-dimensional metric, and you take its trace with respect to this metric here, and that's called theta. Most of the literature uses, no, it's called tau in my notes. Most of the literature uses theta here. I'm using tau because when we were working on this with Ivan Choquet-Bruard some 12 years ago, I told Ivan, well, everybody uses tau, but tau, why don't we use tau? And she said, no, it's tau. So you don't discuss with Ivan, and so this is tau. In this talk, well, in part of this talk, and in the papers we wrote on that. So I don't know why she wanted tau, by the way. She didn't like theta in this context. So this is the expansion scalar, and you have the shear tensor. The shear tensor, you just take the derivative of this metric in the null direction and remove its trace. So that's 1/2 in the, well, there's a coefficient here. 1/2 looks weird. It should be 1/4. Anyway, it should be trace-free. Maybe there's a typo here. And this connection I mentioned to you, right? This is I call it kappa, right? So you just have this null directions is the dr field, and you differentiate it in the null direction, you get this connection coefficient kappa there. The key for all this is the Ray-Chaduri equation, which tells you how tau, or theta, if you prefer theta, but tau evolves along the null directions, and that's really the equivalent of the constraint equations. So the geometric constraint in the null characteristic problem is the Ray-Chaduri equation. So you've heard in Rick Schoen's talk a lot about the space-like constraint, where you have this equation for the Ricci scalar of the induced metric. That's the equivalent of this equation. And so many of you maybe are more familiar with this equation in vacuum, so this would be 0. And many of you might be familiar with this equation where, where the null generators, or these null directions, are finely parameterized. So if dr is if you parameterize these null directions so that the parameter r is an affine parameter, you're going to get 0 here. Well, this is a connection coefficient, so you can change it essentially at will. So if this is 0, then this goes away, and then maybe this looks more familiar to you as the Ray-Chaduri equation responsible for singularity theorems and so forth. But it's important to keep in mind that it is actually something you have the freedom to do. Nobody forces you to use the affine parametrization. And let me mention something which is useful here in this context. So suppose that you have your initial data are such that this tau is non-zero. Right? So this expansion is non-zero. If you think about a light cone, both near the tip, the expansion is non-zero. Actually, it's very big, and both over large distances is non-zero. So there's a lot of surfaces where it's non-zero. Now, being non-zero is actually invariant under reparametrization, because if you reparametrize this thing, you're going to get a positive factor here. But when it's non-zero, you can actually use this equation to calculate kappa in terms of the other things, right? Because if tau is non-zero, you can just divide by it and solve for kappa. So in other words, if you're on a expanding surface, so it could be contracting, but as long as it's non-zero, you can get rid of this constraint in a trivial way than by just viewing this as an equation for kappa. So, of course, if you insist on using the affine parametrization, which is a stupid idea, but I mean you could, then of course you can change it to 0 and you will not be able to do this. But who says that you should? So that's something which shows up in this theorem. So I think that's probably this theorem is essentially telling you the following, that maybe you shouldn't look at the details here, but it's telling you, take two surfaces, give this GAB tensor on them, and if in the case where the trace of the GAB tensor is non-zero, that's all your data. Then you get a solution, no constraints, period. Because by what I told you, you can just eliminate this Raychaudhuri equation. If you don't want to assume that, if you want to have a general statement, then the general statement is here. Take any metric like that on your first hypersurface. So this is your free data, but these functions are completely free to prescribe. You do the same on the other one, and there is a constraint. The constraint is intrinsic on each surface. So you need to give this metric completely free, and this function kappa, right? And this function, if this Raychaudhuri equation is satisfied on each of the surfaces, then you get a solution. If the surfaces happen to be expanding, then you can just forget these two equations. You give any metrics you want here of this form, any functions here, and you get a solution out of this. So that's the simplest version. This version doesn't capture one thing, uniqueness, for a very good reason, that this is really a geometric data. Well, kappa and this is a geometric data, and this is gauge. So in other words, you can start changing coordinates of the surface, and that's going to reshuffle these functions. So there's you're going to get the same space-time with a lot of functions here. And of course, one wants to get also some insight in uniqueness. So and for this, let me skip these slides. Let me go to the formulation of the problem by Randall. And for this, it's nice to use a rigid coordinate system, and one sees better what's happening, right? So in other words, rather than taking any general coordinate, let's use something which I call Eisenberg-Moncrief. You have heard about Eisenberg-Moncrief coordinates yesterday without knowing about it. In all these theorems about Cauchy horizons, the heart of the proofs really relies on this coordinate system that Eisenberg and Moncrief introduced. So here the coordinates are, suppose you have a surface u equals 0, which is null. Well, the claim is that you can always find a coordinate system near the surface, which has this nice form. So this is our famous characteristic data. And the surface is u equals 0. So at u equals 0, this thing drops out. At u equals 0, this thing drops out. And you get this simple form. The metric is minus 2 du dr plus this. So obviously a characteristic surface. So u equals 0 is in this coordinate system obviously a characteristic surface. Note that if you change u, it's not characteristic anymore, right? Because these terms will pop up, and you will not have the, for example, dr will not have 0 length. Now, if you look at the surface r equals 0, then at r equals 0, the induced tensor this term will drop out, and you get obviously a characteristic surface, right? So in this case, this coordinate system is ideally suited for two characteristic surfaces. And these coordinates, Eisenberg and Moncrief call no Gauss coordinates. Gauss has never heard of Lorentzian geometry or no coordinates or anything like that. I think it's fair to call this Eisenberg-Moncrief coordinates, don't mix Gauss into the story. So in these coordinates, then that's Randall's theorem reads like that. So you're giving this function alpha and this metric g. Well, that's not quite how Alan puts it in his paper, but that's my rewording of his theorem. And then you see appearing this form beta. Right? So beta is given on the intersection of the surfaces. So you have these two null surfaces. This is my S, and this beta is a one form on the intersection. And it's a little mysterious to understand it in general, but I mean in this Heisenberg-Moncrief coordinates, it's just this part of the metric. One way to extract it, for example, you just take the metric, you differentiate it, right? You differentiate it, then this U factor will go away, and take U equals 0, then that's going to recover this form here. Again, alpha, right? You can get alpha by taking the metric, U differentiating, and taking U equals 0. That's how it shows up in the metric. And this alpha is actually the same as my kappa from the previous slides, even though it's not obvious. So in other words, it can be set to 0 by gauge transformation and so forth. But so these are the free data in Randall's theorem, and then you have the Raychaudhuri equation where alpha appears here. Now this is exactly the same equation that you saw before in a more geometric form. So this would be the first derivative of the expansion scalar. So that's written in terms of the metric, right? So you just take this metric, and you have this constraint where alpha appears. Again, if this thing is non-zero, you can just eliminate this and you get alpha from this equation algebraically. And then if these are given, then there exists a vacuum metric in a future neighborhood of this intersection. The look version is, well, exactly the same, except that rather than having an intersection here, you get a union, right? So then you get a solution near the intersection. Then we did this in higher dimensions. So that's, again, our theorem in all dimensions. Again, initially an intersection, and then Schlappen-Grossman, we get a union. So that's the formal statement. And boiling down the whole thing to these two data on each surface and this form here, which Christodoulou calls the torsion form on the intersection. So these are the geometric data, and you get a uniqueness theorem in terms of this data as well. Now, I've already told you how to solve this Raychaudhuri equation where when this is non-zero, just algebraically for alpha. Now, so alpha can be gauged away, and Randall proposes to use the conformal class of G. So Alan assumes that this is 0, so you go to an affine parametrization. Then you don't have, whether this is 0 or not, you don't have this freedom just to calculate alpha. But then this becomes an equation if you write a conformal ansatz for this metric G. So you fix this, get a conformal factor. This becomes a second order ODE for this conformal factor, which you can use. And this is actually Sachs already in 62 told us that's the way to solve this problem. So that's Randall's proposition. Christodoulou says, well, let's not do this, but let's prescribe the trace-free part of PRG of this metric as our data. Now, this is a little weird because to know what is trace-free, you need a metric, but he doesn't give you a metric. He tells you what the derivative of the metric should be. So this makes sense if you're looking in a frame formally. So you have a frame, and then in a frame, you know what an orthonormal frame with some abstract metric which is behind, which you don't know. You have a frame, and then you write propagation equation for the frame, and then it makes sense to say what trace-free is, and that's Christodoulou way of parameterizing this Cauchy problem. So rather than giving us free data on this surface as a metric on a conformal class, he tells you take the shear, right, trace-free part of the as the free data. There's another approach, which is Friedrich, which I apologize for a notation which changes from slide to slide, but he tells you take this component of the Riemann tensor as free data. So this is probably physically the cleanest way to think about it. Again, to say what is this component, you need a frame. So he tells you, well, have an abstract frame, and in this abstract frame, for which you're going to write down evolution equations, you give this part of the curvature tensor. This part of the curvature tensor is what is known as radiation field at large distances. So that's a natural thing to have in this context. And then you can use this equation where this D is actually now my shear. So as I said, I apologize for this. Kappa is my kappa, but D is the shear. So you can just solve this equation for the shear. Once you have the shear, you follow Christodoulous prescription. So it's just shifting the data here. So that's another way of doing this, and that's probably justified title of our paper, Many Ways of the Cauchy Problem. There's many ways of setting it up, and it's analyzed in this paper with Tintet. Showed you before. Good. So what can you do with this? So I told you that there are some interesting results coming out. One thing is the following question. Suppose you have you're in the context of the space-like Cauchy problem. So giving yourself your initial data on a space-like surface. So G is the Riemannian metric on sigma. K is the symmetric tensor, which represents the time derivative of the metric. They're supposed to satisfy this scalar constraint, the vector constraint equation. Now, suppose your manifold has a boundary. So now you're in a setting where you have a boundary. And the question is, can you extend this data to a larger set, preserving the constraints, right? So you want to preserve these equations, and the answer is, well, not clear, right? Not clear whether you can do it. There are several theorems about it already under various restrictive conditions on the geometry of the boundary or things like that. And this question plays a role in something called the Bartnik quasi-local mass, where you need to extend a metric on a set to a larger one, satisfying the constraint equation. So this is a natural question to ask, and the theorem is yes. Well, in such a setting, you can do it always, right? So there's no restrictions. If you have a space-like vacuum initial data, manifold with boundary, then there exists a larger manifold, so it doesn't have a boundary. Well, it could have one somewhere else, but certainly you get a manifold in which the original boundary is just in the interior, and there exists, but in the vacuum, if you are sub-vacuum, initial data which extend that. And here's the proof. Here's the proof using the characteristic Cauchy problem. So you take your surface, space-like surface here. It has a boundary. Well, so you solve the Cauchy problem, the usual one, the space-like one, and you get a region of the space-time which looks like that, with a no boundary now, which emanates from the boundary of your initial data set. So you have half of your characteristic initial data here. So to be able to find a space-time, you need another half, right? So you need another half. So what you're going to do is just take any characteristic surface which has the right data. So of course you have to make sure that the transverse derivatives along the surface match the ones that you calculate from your data. But you can certainly do this in even a smooth case. So take any characteristic data which are compatible with the boundary here, you get your surface, and so now you've extended your space-time to the future. That's not quite what you want, because to extend your space-like surface, you actually need data here. But how do you do this? Well, that's pretty easy, because what you do, so you have this piece of hypersurface here. Now you take any, but essentially any initial data, which are characteristic, which emanate from this point, and which are, which smoothly join to the ones you have here. You solve to the past. Now with the Randall theorem, you would have a problem, because you're going to get neighborhoods here. You can't really connect this. But with the Look theorem, you can go all the way and get a neighborhood, a path neighborhood of this surface. So now you get a space-time which satisfies the equations and which extends your data. Well, you still need to make sure that it extends differentiably, and this is and it does so because there's derivatives to this surface, and that's the key of all the constructions I'm going to present you shortly. The transverse derivatives of the metric on this surface are determined by transport equations along this surface, and the transport equations are reversible. It's ODEs, so if you take your ODE and go from here to there, if you go backwards, you're going to get the same solution. So you're sure that the transverse derivatives in both directions are the same, and you get it. If everything was smooth here, you're going to get a smooth extension, and you can extend your space-time like that. So that's something I certainly wasn't aware of until we wrote this paper with one sitting there a year ago. So that's one application of the non-characteristic Cauchy problem. Certainly not the most spectacular one. And so let me return to this Aretakis-Timmer-Grodniansky question. So one space-time here, another one there. Can you just connect here? And the first reaction is, obviously you can. If the free data are just a metric here and a kappa on this surface, and you have a metric here and a kappa on this surface, then you just take anything which interpolates, and you're done. But this forgets about the fact that you need not only to match, if you want to match these space-times, well, you need to match continuously the data on the surface, but you also, in this space-time, you have not only this metric here, but you have its transverse derivatives as well, right? So you have the data, but you have all transverse derivatives of the metric on n tilde 2, and here you have all transverse derivatives in this space-time. So when you want to have a smooth space-time, you not only have to match the data, but you have to match the data here so that the transverse derivatives match, and that's the difficulty. Let's see how this works for just wave equation in Minkowski space-time. One sees all the where all the problems are, right? So just take the standard wave equation and let's introduce double null coordinates. So this would be u equals 0 would be here, and v equals 0 would be here, and so this is t, this is x, and y and z are in the other direction. So that's your characteristic Cauchy problem now, right? I just give data here, try to find a solution. I hope my -2 here is correct, because it's always a pain to do this complicated algebra, but I think that's what you, if the coefficient is wrong, then apologies, but I think the -2 is correct, yeah. So in other words, this thing takes this form here, and then the initial data on each surface are just, you give the field on your surfaces here or there, and now this equation is actually a transport equation at u equals 0 for the transverse derivative. So d phi over du is the transverse derivative here. And you can solve for this derivative by NODE along the scale. So that's and this is determined by the initial data, because this is phi on the surface is known, right? So you can just calculate this, and you integrate if this is u equal to 0, and this is have it right. This should be so this should be v1 and v0. So sorry about this, right? So this should be v0 and v equals v1, and we integrate fu equals 0 in v. So there's sorry about this. It should be u equals 0 and v1 v0. So you just integrate this, and you get the solution. By the way, notice the following, that to get one derivative, one transverse derivative on this side, you need two derivatives of the initial data. So that's a property of the characteristic Cauchy problem, that to have one derivative of the solution, you actually need two derivatives in initial data. Two derivatives of the solution, you need four derivatives and so forth. So it gets, so there's a lot of loss of differentiability. In the standard Cauchy problem, you start with HK data, you get an HK solution. Here, you start with HK data, you get at most K half solution. So you can integrate and you get this this equation here. And you can keep differentiating this in u and get the other derivatives, right? So if you can, if you do it once, you know what the derivatives d phi over du are on the surface, and then if you can just iterate this equation, and when you know what the eth derivatives are, you know the e plus ones, right? So all the derivatives are determined by transport equations. And so now if you go to this picture, well, you need to, because the transverse derivatives are determined by transport equations, you need to make sure that the data you put here are such that these things match, right? So this thing, this is known from the data. This is known from the yellow space-time. Then this is known from the green space-time, right? So so phi here has been such that these things match, right? So that's a control problem. You need to solve this control problem, and this is in the case of the simplest wave equation, but Einstein equations would have a similar flavor with considerably more complicated equations to analyze, right? So this is the question. Can you adjust the free data between the surfaces, or at least a finite number of them, right? Maybe not an infinity, go on a smooth one, but a finite number, so that you get a smooth solution. Now, there are constraints, and the constraint is simplest to see if the free data are compactly supported in this direction. Because if they are compactly supported in this direction, you look at this iterative scheme, that the derivatives will also be compactly supported in this direction. So now if you integrate in the transverse direction, this equation, right? So you just add an integral here on R2, then this integral, well, there's a Laplacian here, right? And so if you integrate the Laplacian on a function which is compactly supported, well, integrate by parts, you get 0. Right? So this thing is, if you take this equation, integrate by parts, you get 0 here. So you get an abstraction. If the integral of this derivative does not match the integral of this derivative at at these junction points, right? So you have an integrate in the transverse direction. If these things don't match, you're not going to be able to do it. And also, it's trivial to analyze for the wave equation, but now it's so you need to do the same work for Einstein equation, which is a bit of more work to be done. So and good. So there are the theorems, right? So Aretakis, Megadoniansky tell you that you can do it near Minkowski spacetime. So now your initial data surface is you take a light cone in Minkowski, where you don't want to go all the way to the tip because shell breaks loose at the tip. So you just take R1, R2 here, and data which are near to Minkowski here and near to Minkowski here, and they show you that you can do this gluing with two derivatives. Right? So with two derivatives up to a 10-dimensional space of obstructions. So this is the case where you look at Einstein equations. Lambda is the cosmological constant 0. The mass, well, the mass, think of the Schwarzschild mass or something like that, would be 0. Then you have a gluing theorem. Now this C2 is really at the level of initial data. And if you start thinking about the space-time you get out of this, it is really not clear. Because remember what I showed you, that each derivative in the solution needs two derivatives in the initial data. So on the face value, if you can do it with two derivatives here, you can at most get one derivative in the space-time. So if you just try to think naively in terms of the known theorems in the literature, the space-time you're going to get out of this is a disaster. Maybe it's going to be you're going to get one derivative in a Sobolev space, but in a Sobolev space, if you want to get classical differentiability, you're losing differentiability. So just naively, you're going to get the distributional metric. So what can you do with the distributional metric? Well, I don't know how to do this. Now, if you're a little more careful and start thinking about this, you can probably get a C1 metric out of this with a lot of work. I'm not sure, right? But really, this C2 here is a problem. If you want to do anything with this construction, you really need more derivatives. And that's what we did with Wan and Finian Gray. So that's a paper on the archive in January this year. So you can do it for any derivatives. So you'll be working at Birmingham Kotler metrics. I'm going to show you what these are shortly. And you probably want to assume that the mass is non-zero, because mass equals 0 is always a problem in GR for gluing theorems. So you're saying that you're near one of these Birmingham Kotler metrics with non-zero mass, and you get a space of obstruction, which is interesting, which doesn't grow with the number of derivatives. So if you think about this problem, you solve your equation, you have your transport equation. This integral has to match this integral for every I. Right? So for every I, you're going to get one more constraint here, right? Because you get a different operator at each stage. Right? So in this linear case, the number of constraints will grow with the number of derivatives. Well, somehow, if you assume, and that's important, that you are near this Birmingham Kotler matrix with M non-zero, you can actually do it without a growing number of obstructions. So what are these Birmingham Kotler metrics? Well, here it is, right? So that's first you allow a non-zero cosmological constant, and so this alpha here, which has nothing to do with an alpha in one of the previous slides, is just a constant proportional to lambda. So if lambda vanishes, then this would be 0, then this term will be not there. That would be then the no cosmological constant case. So think about this metric is alpha equals 0, this is gone. think of this metric as k equal 1, then this is just the Schwarzschild metric in higher dimensions, right? So our theorem says if you are in asymptotically flat case near a Schwarzschild metric with non-zero mass, then you can do the gluing in any dimension. But you can do it with a cosmological constant. This works as well. And when you have a cosmological constant, you have another free parameter here, which is associated with the scalar curvature of this metric. So if you're in a sphere, then this would be an Einstein metric with kappa equal 1. If you are, but you can have flat metrics here, you can have a negatively curved metric here. The construction works. I just want to emphasize that, of course, it's nice to have a higher, topology, which is essentially arbitrary and arbitrary lambda, but I think the key of this theorem is really that you can have this k as big as you want, and therefore the solution you're going to get out of this is as differentiable as you want. Doesn't work for infinity. We don't know how to do it for infinity. That's an open question. That should be, but certainly if you want a C200 space-time, then you probably need this k to be 400 or something like that. But the data will be glued at 400 level, and the space-time will be glued at. You'll get a space-time which is 200 differentiability. I don't know how I'm doing with time. Is it over already or? Very good. Okay, good. So that's the theorem, and I promised you some more applications of this. So that's a beautiful new application which has to do with something called the third law of black hole dynamics. So formulated vaguely by Bardeen, Carter, and Hawking, a black hole with zero surface gravity cannot be formed in a dynamical process, whatever this means. And zero surface gravity is zero temperature, so this is supposed to be a law of thermodynamics, right? So you cannot achieve zero temperature in a dynamical process. Well, Keller and Unger 2 years ago have shown that this is wrong, right? And then the construction is using this null gluings, right? So they can construct a space-time which dynamically connects to a zero temperature black hole by doing this null characteristic gluing. And so they have a scalar field, and they glue to an extreme Reissner-Nordström. Another beautiful theorem is just black hole formation. Well, there's this monumental paper from Christodoulou which shows that you can form dynamically black holes in vacuum by a very sophisticated construction. Of course, this theorem of Keller-Unger bases on many ideas which have been since which are based on this Christodoulou paper, but you can use this gluing to show formation of black holes in vacuum. And again, this is an all gluing now, and it's 30 pages compared to the initial 600 pages of Christodoulou. And well, Christodoulou didn't quite construct black holes, so there was another 70 pages by Lee and Yu to show that you actually can construct black holes using Christodoulou's construction. So of course, it's not a question of comparing the number of pages, but I think there is a real new insight into the problem by doing this construction, and I think I'm probably